Hello, everybody. Welcome to this week's episode of Frivolous Gravitas. Today, we're going to be letting Chris take the lead in a discussion about nuclear energy. We will be looking at why it's probably the most promising form of energy that we have at the moment. That goes for fission and fusion right now. Fusion's been in the news a lot, but fission, even though it's about 70, almost 80, 75 years old now, has shown a lot of innovation in the recent actual decades, but none of it has been put into place due to some fears that were in the past, frankly, quite legitimate. Everyone thinks of 3 Mile Island and Fukushima and Chernobyl, to name 3. But when we look at these in comparison to other natural disasters, such as, say, a coal power, then we see that there's a little more to this story than we originally thought. And there's a lot more light and promise with these technologies than we are not being led to believe, but so then we are being, I guess, than we originally thought. They're not the scary demons that we had. So with that, we're going to go into why these technologies essentially and how they work and why we should be looking at them and seriously and kind of taking off our, hats of fear and, giving them a decent shot at implementation. So with that, I'm going to let Chris get the ball rolling.
Cool. Thank you, Jordan. And welcome everybody to Frivolous Gravitas. I'm going to start off just by a quick overview of what we're trying to achieve with a fission reactor, like a nuclear reactor, the power plants that we're all familiar with these days. And then, being that I'm not a nuclear physicist, I will do my damnedest, though, to try and walk us through the steps so that we understand, not so that we memorize it or that you study my words, but just to put some context around the safety issues and the environmental concerns and everything that we're going to be talking about afterwards. So to start off, we're talking about the smallest parts, but the energy we're getting out of these reactions are based on the strong nuclear force that binds atoms together. And when they split, they release energy, and that energy is what we're trying to capture in the form of heat.
Don't you mean, sorry to interrupt, don't you mean, because an atom is one particle made up of elementary particles, protons, neutrons, and electrons, and that's what we're splitting, right?
Yes.
And which makes an atom, which when atoms come together, then you get a molecule.
Yes, yeah, sorry, I thought that's what I said. Yeah. Bundles of atoms make molecules, and bundles of molecules make...
Yeah.
Anyway, that is correct, yeah. So what we're doing is splitting atoms, and that takes one element, and then it produces separate elements. So either 2 or more other elements split off of one element, and it's the energy that's released in those bifurcations, those splits. That's the energy we're going to try and harness that heat, throw it through a heat exchanger, heat up some water, water turns to steam, steam turns to a turbine, which we're all familiar with, and that's how we get power. So the idea is basically to try and sustain a chain reaction without it going overboard. So without it, a bomb is just a chain reaction that's completely unmitigated and it just expands and explodes. So we obviously don't want the explosion, we just want sustained continual degradation. And that's what the power plants do, is they make those controlled reactions happen by having a very controlled environment for the atomic processes. So to start then, I guess, we'll talk about the simplest designs, and we'll use the basic design just to explain the key concepts and why there's so many types and designs of nuclear power plants. So the simplest design is using water and uranium. Now, the reason we use water is because it can act as both a coolant and a moderator, and it's also the heat exchanger, because water is a great exchange medium for heat and producing steam to turn a turbine. Because water is incompressible, you can really heat it up and get a lot of energy out of it. So it's useful on all fronts, and it keeps it really simple. And these are the earliest designs are using water like this. But the problem they ran into was to sustain a good fission reaction with uranium, they need to heat the water much past the boiling point. And to do that leads into the first biggest problem with all nuclear reactors of this type. And all the disasters that we speak of, like Fukushima and 3 Mile and was the other, Chernobyl?
Yeah.
As our popular ones, those all happen because of the pressurized water. So when people say there was a nuclear explosion at these plants, it's not true. It was a gas explosion because vapor gas of water, when it changes phase, its volume expands by an order of magnitude. And when you compress it at 3 times the boiling point and then suddenly release it, it looks a lot like an explosion, releases a lot of energy, but it's not a nuclear blast by any means. It's a water blast.
Right, because a lot of the fear comes with because nuclear catastrophe is still kind of in the public mind. Probably not so much as during the height of the Cold War, but you imagine, they're going to put a nuclear reactor beside me and it's going to explode, and I'm gonna sorry, my cat. It's going to be like that scene in Terminator 2 or whatever. And what ends up happening is that, the water isn't controlled properly, as you say. And then there's nothing to mediate the fission process. And then then the failure leads to that fission going out of control, but it just ends up releasing a bunch of radiation instead of just going.
Yeah. But it's important to note that it's not the nuclear reaction that's exploding in these cases. It's the pressurized water system that's being breached. Right. The water that's used as a coolant and the moderator and the power, all of that is just expanding into gas, and it does it with a lot of force. So it looks like a bomb, but it's not a bomb. It's nowhere near the Beirut explosion when they do happen.
No, or the Halifax explosion if you're on Canada.
Yeah. But we'll get into other safety, because that's not the only safety thing, but it is the biggest. And it's just for people being cheap and using the oldest, earliest designs that we have that problem at all, as you'll see later. Mm-hmm. So the Earth has a lot of uranium in it. Most of the uranium that we use for the reactors are, I think, 238, and 235 is the better uranium. But if you use just 100% enriched uranium 235, it just the fission reaction happens too quickly, because fast neutrons and slow neutrons can cause fission. Whereas with the 238, it's mostly just the slow neutrons. So one of the key concepts we'll talk about with the design of nuclear reactors, we discussed the coolant already. The fuel, which is the uranium. The moderator is what slows down neutrons so that they don't escape the process. Like, you want to capture as many as possible, first of all, and you want to use as much of the fuel as possible. So with these old reactors using about 5%, I think, 1 to 5% enriched uranium to 95% to 99% just regular run-of-the-mill ground uranium. And they use that blend to kind of make sure that the slow neutrons and the fast neutrons are balanced enough that the chain reaction happens, but it doesn't escape. So basically, when you have fission, a neutron hits a uranium atom. When it splits, it decays and produces usually 2 more neutrons, sometimes 3. But you get into the problem where if you have high heat, high pressure, and highly enriched uranium, then you get sort of bombs grade or like weapons grade plutonium does the same thing, where you'll get 3 neutrons regularly. So they'll split 2 more atoms every time. and it just exponentially expands. So that's sort of what you want to avoid in a nuclear reactor, just for regular power.
So the moderator will slow down the reaction. And
it'll slow down the neutrons. So the reaction could still be just as fast if you had a different fuel source which we'll talk about too, because thorium is a lot like that.
Yeah.
So only in the case of this type of reactor does that matter, but every reactor is going to have a moderator which slows neutrons, coolant, fuel, and then obviously safety, discharge, and stuff like that. So I'll post some infographics. Actually, I did a couple. It might be easier for the listeners to get a link to some images, charts. But large nuclei like uranium and plutonium, they release neutrons when they split, like I said. Those nuclei can be split by colliding with free neutrons. So if a neutron splits uranium, releasing energy, and 2 more neutrons come out, then more uranium is split from those 2, thus the chain reaction. So this is what we call critical mass, and that's when enough fissile material is present for a runaway chain reaction. So with that said, we'll set the stage such that each split of the atom from the neutron colliding with it only takes 1 single neutron, but not every single time do they split from a neutron collision. That's why you need 2 with a little bit of probability of 3. Because every now and then a neutron will get absorbed by the fuel rather than spit out or split. And that's just quantum mechanics probabilities. There's no real way around that. And that's sort of where a lot of the waste comes in from nuclear reactions. The waste products are usually from an absorbed neutron instead of a fission. Mm-hmm. Another term we'll use is fertile material, because a lot of the reactors that we're building today are breeder reactors, and that means that the fuel source or the blanket around the fuel source, like part of the design of the nuclear reactor, the blanket they call it, when it hits a stray neutron, it actually produces more fuel when it absorbs its neutron. So it's just another, we'll talk about it a bit more later after we get through the different designs, but just for the basic design, I'm just pointing out that there are a couple more factors, but they're not as pertinent to the discussion. But fertile just means that a neutron reaction creates more fissile material, and fissile just means that it's capable of being split when a neutron hits it. That's our fuel, because we get the energy from the split. So uranium-238, pardon the papers, is more stable than uranium-235, so it needs fast-moving neutrons to sustain its reaction. That might be in contradiction to what I just said over the top. I get the numbers confused, and like I said, that's why you shouldn't study from this. It's just to give you an idea of how things work. I'm not a nuclear physicist. But,
neutronologist.
Nucleologist.
It's pronounced nuclear.
Nuclear, yeah. I was going to comment too, actually. Way to do it properly. Can't stand that. Anyway, so U-238 will actually absorb thermal neutrons and convert to plutonium-239, which is also highly reactive, so that could be said to be kind of fertile in a way. Enriching fuel to increase the ratio from U-235 to U-238 is the best way to buck the reducing cost and waste and maximizing stable energy output. So it's not just that you want the reaction sustained. When you use cheap thermal reactors like these, they produce more waste and they don't use all the fuel. So most of the uranium that goes into these old reactors, these thermal reactors are just another word for the water cooled, moderated, and powered. They're all powered by steam, but the cooling and the moderation through water is specific to a thermal reactor. And that's why they need to be pressurized. But enriching uranium, I guess I should explain that too. It's when you put uranium in a centrifuge and you spin it around so that all the atoms, electrons line up to one side. So you're sort of producing a highly enriched on the inside, and then you can extract that from the less enriched part on the outside, and then less enriched part on the inside.
Right.
It spreads out, centrifugal force. Yeah. Newtonian physics, look it up. So I'll just describe the moderator again quickly, just so it's a bit clearer because I might be kind of bouncing around here. But there's only like 3 or 4 key concepts. So if we drill these in, then we'll be able to go forward understanding better what the options and availabilities are. So the moderator, in this case, is water, but graphite is another common moderator, anything that slows down the bounce of neutrons flying around in the core. It's used to get the most out of the uranium-235 to the uranium-238 mixture. As I said, you don't use just a purely enriched fuel because that would just be bad news. So it's usually a very small amount of the enriched stuff that you need. Hydrogen atoms in the water, the reason why they're helpful is because they're about the same mass as the neutrons. So neutrons bump into them. They don't react to them. They just get slowed by them. It's like kind of shuffling through a crowd, basically. It doesn't work with all elements, but you can do it with liquid metals and liquid salts. And again, we'll get into that in a little bit. So they impede or slow neutrons in the absorption in U-238. Water also works as a great heat exchanger and coolant, which we've already discussed. So this is currently called the light water thermal reactor. Most people call it just a thermal reactor. And it's one of the first that we decided to build because of, you'll probably know more about the history of it, but it works well in nuclear submarines because submarines are surrounded by water. And these things are self-contained and kind of small. They could be smaller, but the high pressure, the pressurization of the water is what makes these reactors need to be so big. And then you need like a containment zone around them just to make sure that if they do explode, they don't bust out people's windows and kill babies and stuff. So the problem with 3 Mile Island was water escaped a jammed hatch, and that's what caused the breach, which led to rapid expansion of the gas and the so-called explosion. Chernobyl was water boiling slowly. Chernobyl was the water boiled, and then because it boiled, there was less of it to moderate the flow of neutrons, and that's what caused the escape or the breach in the Chernobyl incident. Right. And the Fukushima one was because the power generators that are supposed to keep the control system working were wiped out by the tsunami. So requiring electricity to maintain your stable, non-explosive power plant is a bad idea. And again, we'll see that in the molten salt reactor variants because they have a passive versus an active system. Whereas if power gets cut off, electromagnets drop the fuel rods, those fuel rods go in, and if it still keeps overheating, a plug melts, everything drains through the plug into a containment vessel, and there's no explosion, no runaway heat, no problem.
Yeah.
That said, more people die every year from air pollution caused by coal than do by power plant failures or meltdowns. So that's why when we say it's relatively safe, scientists are always very meticulous with their words and saying it's not perfectly safe. But the public perception of that is to misinterpret it, thinking that, they said it's only slightly safe or relatively safe. No, it's very, 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 very safe.
Well, there was one statistic I came across that like more people have died putting up solar panels than have died in all of the nuclear incidents combined.
Yeah, that's a good one.
So,
and there's another one, the asthma caused by even natural gas, which burns relatively cleanly. The asthma alone caused by natural gas has killed more people than all of the nuclear power plants breakdowns combined. And those power plant failures were entirely preventable had they just not been cheap in the design.
Right. Well, and the Soviet Union was very renowned for their their miserliness with regard to infrastructure. So,
and they're not very adventurous with new designs either, because there's an expense involved and time fixing unforeseen problems. But I mean, in the long term, it's really worth it. But when you elect a new president every 4 years, there is no such thing as a long-term plan.
Right. We can get into also with that. We can get into sorry, my brain is a little
no problem.
webby, right?
I was just going to go into the molten salts and molten metals just to describe the difference between the thermal and the not. And then I think
Right.
we'll go from there.
Yeah. So with a normal reactor, essentially what it seems like to me, so let me just try and layman it for anybody, is that you have radioactive rods or material in a rod, and then you dump it in a you dump it in a pool of water, which it'll heat up. And then, because one of the things is, you have this big building or this, container or this, thing. It's got that, evil looking symbol on it.
Big smokestacks.
Yeah, some giant smokestacks. And then what happens is you start to think of this again like a car or something. It's this magical thing. But all that's happening is that you're just using something different to heat up the water. It's the same way that we produce energy from coal. You heat up water with the coal. It's just this method of heating up water is just way more efficient than any other method we have at the present moment. You get more out than you put in. The problem is it's a lot more complicated because, there's a lot more science involved than just light the rocks on fire. So
yeah, but that's bound to be the case with any complex system.
Right. So what happens is you get that heat. You're turning this atomic energy into these atomic reactions, the energy in that, and which heats up, which is transferred into the water, which then is transferred into kinetic energy in a turbine, which is transferred into it's like a magneto, which changes that into electricity, which then sends it out. It's a lot more complicated than that, but that's it.
It's not much more complicated than that, though. That's pretty bang on. And the thing is, the fuel source only needs to be these tiny pellets because we're talking about like atoms splitting atoms, right?
Right.
And that's one of the benefits to it. And the fact that we're using water to power the steam, it just acts like a normal heat exchanger like a radiator heater does. A radiator heater is a heat exchanger from a hot metal pipe to the air in your room. It's the same thing, but it's just water on both sides.
So to me, what makes it complicated are, one, in the Soviet Union, we want to power all of nation. So they just make them huge and we don't care. Put them up. I don't care. In America, you say, oh, we like power, but there's already an industry. So we'll tentatively go into this. Same with Canada in the 60s and 70s, where they wanted to build 22 of these. I think one of them is still online because of the backlash, which we will get into. But what happened in the West here was that you get, I don't want to sound like a complete libertarian, but you get a lot of government interference saying, oh no, now you need to do this, you need this safety procedure, you need that safety procedure. What happens is you end up with a stunted development process. So now we're stuck with these reactors that we're talking about is technology that was designed in the 50s. And we have it in our head that these are the only reactors that we can use. This is nuclear technology. We need to get fission right, or fusion right, because fission is it's a lost technology. It doesn't work. Well, the problem is that we haven't been innovating on this, and probably been going back because since the 50s, because there hasn't been allowed to, because innovation in this field is very, very expensive. Essentially what you have to do is, to get a nuclear reactor approved in the States, you have to have the entire thing approved. You can't make any changes along the construction process because, there's safety procedures. It has to be exactly as it is. So what happens is, even if you learn something, you can't implement your new knowledge from the construction into that new one to make it more effective. You have to settle for 10-year-old technology or 15-year-old technology, because that's how long it takes to actually build one of these things. So,
and that's one of the biggest drawbacks too, is that because they're so complex, and what we're doing is, again, controlling a nuclear reaction. That's insanely complicated. But once it's built, it works. That's the thing. But it's the cost, the upfront costs are like 15 to 20 years before you get paid back on them. Whereas if you put up a wind turbine, it starts making you money the next year. Or if you put up a coal plant, 3 years, it starts making you, starts making it back. I'm not saying it's a net profit, but you get nothing while it's being built. Like absolutely nothing comes out of a nuclear power plant for like 10 straight years. Whereas everything else that you can build it, you'll start generating power within 3 to 5.
But the innovations we're going to be talking about, and Chris is going to be about to get into, I'm going to just a nice little segue for you, is that some of these innovations make it cheaper, easier, smaller, more portable than, this big, multi football field spanning, eyesore on the horizon. So why don't you talk about what we've learned in the last 50
the funny
years.
thing is we learned this at the same time, roughly speaking, as we learned how to do these thermal reactors with the pressurized water. Like we learned the better way right away. We just never built them. And it's not like some under the table or backroom guy who nobody knew. The guy who invented the other process, Alvin Weinberg, also said that, wait, there's a better way. Do this. And they just didn't. So I'll get into the other thing that Weinberg suggested we do right from the start back in 1955 or something. I've got the date in my notes somewhere, so I'll probably stumble across it during the show. But so molten metals and molten salts are what we're looking at now. And again, the big thing about the size of the reactors was the pressure. So once we don't need the pressure anymore, we can have smaller reactors, first of all. Second of all, they won't explode when they breach. Molten salts will act as your coolant. And that means, it's kind of weird to think about it, but when you melt a salt or lead or something like that, when you get liquid lithium, liquefied metal, you can use that to cool a reactor that runs hotter. The hotter reactor core is going to give you much better power efficiency for the fuel you put in. So point number one, way less nuclear waste. Point number two to that is operating at higher temperatures is more efficient, so you get more power for the space, which is a huge plus if you're building these giant monstrosities that cost like billions of dollars. They remain liquid, but at a breach, once they're released into natural air or they cool, they harden. So they actually solidify and self-contain in the event of a nuclear meltdown, catastrophic failure. Worst thing you can imagine, somebody bombs the thing and it just busts open. All the nuclear or all the molten salts and metals that are used to circulate the system and keep it running will just harden and freeze. And it'll be a mess to clean up, but it's not like it's going to get into the air into a vapor.
Right. And even if a few neutrons do exit, it's probably so like during the, I don't know how quickly molten salt or whichever salt they're using here would I don't know how quickly this molten salt would thing, but it's not going to let all the neutrons out. Like, if you watch Chernobyl, it cracks open and all the neutron streams just come, like all the neutrons are just flowing out of the reactor.
Yeah, and it's radioactive water too, and that water is airborne. Whereas these molten salts will never be airborne because A, they're heavy, and B, they'll solidify and they'll contain all of that nuclear waste inside of the...
Right. So this is what you mean by a passive system. It does it automatically as part of the system itself. And with a passive system, so, oh no, it got hit by a truck and now it's a broken reactor and you end up with just an, oh no, instead of well, I guess this is it.
But then people actively have to prevent a worse failure.
Right.
So that's
on top of a really good passive system, you can have, whatever active systems you want. You can make that redundant. So
yeah, you would.
In effect, whatever safety procedures you want would be just icing on the cake. Now, that's not to say we shouldn't do that. Of course, we should do that. Mm-hmm. We should make these as safe as possible, but we should also, we don't want to start wrapping them in bubble tape just because, more safe is better. It's like, no, at some point you have to measure safety as an expense. And at some point, if you're saying, okay, this makes it 0.00001% more safe, it's like, let's not spend our money on that. Let's start spending our money on plugging it into things or something or new.
But the thing is, with this design, you'd actually run out of ideas to even be more redundant because it already self-contained. There's nothing you can do to hard metal to make it harder and more metal. Like it's already the thing that you're trying to do.
Well, you run into new
the
problems.
breach is going to be more dangerous. The bomb that hits your reactor is going to cause more harm than the reactor exploding from it. Because
Well, my thought is that theft becomes a problem because these things are now small.
Well, they're not that small. They're still 75 feet high and like 15 feet wide. So
I keep hearing upon when I was doing some, amateur research when I was reading, essentially, that a lot of people are saying that these things can be made to be very, very small. Now,
they can be, but they're less efficient. You want that really high heat, and to get that high heat, you need your containment vessel to be able to sustain that high heat. So it has to be a really thick containment vessel and like super heavy. So it is possible. I'm not saying it's not possible. It's just, it's not feasible. It'd be way easier for them to just build their own centrifuge and mine their own uranium than to steal one.
So
plus they're put in and there's water everywhere. Liquid metal is kind of hard to move.
Yeah.
So
carry on.
Okay.
Sorry.
No. I'm glad you're helping me. You're helping me think. Where was I though?
We were talking about molten salt reactors.
Oh, yeah. Okay, so the other thing is with the safety precautions, not just in the event of a breach without the pressurized system being capable of exploding, you also have the added effect that because you're running a really high temperature nuclear reactor, the thing that was preventing us from running more efficient, higher heat was the water that we were using. But when you use a liquefied metal, the molten salt, they can run at higher temperatures, but that also means that in the event of a chain reaction or critical mass and it goes too hot, in a meltdown event, the plug at the bottom of the core will melt itself. So the plug melts from overheating and then drains into a containment vessel underground. So absolutely no chance of contaminating the air or the earth or anything, because that containment vessel is going to be built to, all it does is cool things down. And once the fuel's out from the liquid metal, then there's no neutrons to produce more reaction, so there's no more heat being produced, and it calms itself down. That's again part of the passive safety features of this type of reactor design. And Alvin Weinberg was like insistent on this part alone being enough of a factor to stray away from the high pressurized thermal reactors in favor of the molten salt reactors. So I'm going to talk a little bit about waste before we talk about thorium, just so that we get the basics covered first, because I think it'll be easier to...
Because one of the things that keeps coming up when we talk about nuclear power is, well, what do we do with the waste? I don't want that. Like, you can't get rid of that. You know that there's nothing we can do. All you can do is, bury it in the sand somewhere, and then it's just going to pollute that area. Or we can like it's expensive to shoot it into the sun, which I think would be awesome. Or like send it to Jupiter. I don't know. But
if you can get nuclear powered propulsion to push it into the sun, it might be feasible to do it. You know what I mean?
Right. But at the same time, I do agree that mentality of, well, we'll just throw it away, is like, I tend to even do that on my small scale. Like in my house, I'll just be like, this is organic. I can mulch it and turn it into soil and grow things in it. Why would I waste it? I don't want to just, it's not useful, so I'm going to throw it away. And I personally don't like that mentality, because I'm kind of a closet tree hugger. But at the same time, I think that mentality also shows a lack of, creative thinking. Like, we have this material and we're going to have a lot of it. What can we do with it? Let's put some thought into that. And I think a lot of people have.
But again, that was only ever an issue because we used the wrong reactor design. Like, we chose the reactor that only uses 1% of its fuel. So we're going to have more waste. And that was just because of wartime mentality and nearsightedness, like political myopia, as I call it.
Well, and a lot of, like, around the time that this, where is his name? I got him here. Weinberg. When he became director of the laboratory in 1955, the world had just seen about 10 years previous, 2 nuclear attacks on civilian populations. And it had in its mind as the Korean War had just ended, where tactical nuclear weapons were a viable strategy of offense on armies and bases and whatnot.
Mutually assured destruction.
Yeah. Now, it's almost one of the things that almost probably saved us during the Korean War. Argue in the comments, but the fact that the Russians had nuclear weapons saved the world from a nuclear war, because the Americans might have used them again in the Korean War against the North Korean and Chinese troops. So, but nobody would have been able to retaliate, but that would have also, that's the use of nuclear weapons in war. We don't want to get used to doing that.
That's how you feed terrorism for generations.
Right. So what ended up happening, and rightly in people's minds, is that they became afraid of nuclear stuff, but they didn't know what they were afraid of. And we see this today. People don't understand the things they're afraid of. There's things that even when you do understand, you can still be afraid of them. Mm-hmm. And that nuclear weapons are one of them, but nuclear reactors, you were cast in the same mold as that. So they nuclear reactors can explode, and it'll just be I don't want my town to become another Hiroshima.
Yeah, and that's like comparing a controlled, sustained reaction that's built to go slowly with something that's built to expand as quickly as possible. Right. Apples to oranges.
How can we release as much energy as possible? Well, let's just put a bunch of TNT in a steel case.
But the fears are legitimate, but they're not relatively sound. And that's sort of what I want to dispel today in talking about nuclear waste. Because first of all, like I said, the thermal reactors only use 1%. So that creates 99% of all that you bring into the factory comes out as waste. Mm-hmm. That's ridiculous, first of all. Second of all, part of the byproduct, sometimes when those neutrons are absorbed, rather than causing fission and energy, if they're absorbed by the uranium atom, they convert to plutonium, which is also a fissile material. So rather than creating weapons, which is the main reason they stuck with this design, is because they were going to use the byproducts to create weapons with it, which we don't want more nukes. But that's why we have such a huge nuclear arsenal, is because we chose a design that was ready to create plutonium for us. Right. But you could use that plutonium in a reactor right next door and create more energy with it. So the nuclear waste that everybody's worried about is caused by our ignorance. It's not inherent to nuclear power. It's caused by the fact that we wanted to produce weapons. That's the reason we have these inefficient designs.
And now that we're slowly, getting rid of a lot of these, with taking a lot of effort, but
there's international agreements to de-proliferate. Yeah. I don't know what the word for that is,
but nuclear proliferation treaties. There's a bunch of them.
But they're trying to de-proliferate. They're doing the opposite.
Yeah. And so what...
Non-proliferation, that's what it is.
Yeah.
Sorry.
So what was happening? Well, I guess the standard way of dealing with this waste is, I don't know, sticking it into bullets or something for the A-10s. But essentially what they do is they put it in drums and then put those they stick it in concrete and then put those into drums and then bury it deep in the ground. But is that the only way of dealing with this?
That's actually the worst way. Water is a fantastic containment, and you don't want to pollute your water sources with it. But the reason why the Europeans dropped it in the ocean wasn't just to get rid of it out of sight, out of mind. Water is actually a really good place to store nuclear waste, because then the radioactive byproducts don't escape the tin can that you put it in. Mm-hmm. So even though they're leaking and stuff in the ocean, it could be a lot worse. They could be leaking into soil, and soil is naturally porous. So it spreads, and contamination is very, very hard to contain once it's in soil, because you have to dig up all the soil all the way around the contaminated area. Mm-hmm. And that's extremely expensive and very energy intensive. So you're going to use a power plant to produce more power to contain the nuclear waste produced by the power plant. So it's a negative feedback cycle.
Right. But
or
See,
positive feedback cycle.
is there any, like, I'm assuming like there's different wastes for different types of reactors. Is there any uses for these materials that we know of?
There is, but the easiest way to avoid it is just to make less of it. Don't produce 99% of waste from your fuel. Secondly, you can recycle it. So take the fuel that is spent and radioactive. You can put that into another reactor and create more power, and then its fuel will be smaller because you've extracted energy from it all this time. So the waste then gets reduced by reusing it. Another factor to consider is the half-life of the byproducts. So in a thermal reactor, you're creating half-life products that have like 300,000 year light time to decay. So they're radioactive and dangerous for like 300,000 years. Whereas if you use a thorium reactor, you create so much less byproduct, and we'll get into that in just a minute after we talk about waste here. But it creates so much less byproduct. And the byproducts that it does create only have a half-life between 100 to 400 years, which is a long time. But I mean, a concrete structure can last 400 years, so you can put it underground safely and it'll never bother you in a cave or an abandoned mine or something like that. You just fit the mine to suit it. You don't just dump it into a dirt hole. But I think Finland or something's doing a huge storage facility right now underground. It's like a 10-year plan, or maybe it's Norway. I can't remember exactly. Maybe you can look that up while I describe thorium.
So,
but there's a huge underground storage facility that's being built out in Europe right now.
I came across this that essentially says that a lot of what's happening is they're recycling 97% or 94% of what's going on, and then the rest, the 4%, are immobilized by mixing them with glass through a process called vitrification. So these guys aren't, like, they're not just dumping it in the ground, and they know what they're doing. They're not just being like, oh, don't need this anymore, let's just dump it. So
they did used to do that, and the Russians, I'm pretty sure, did that, but we don't anymore because this isn't 1960.
Yeah, so we can't just say, we can't just be righteously indignant about this. So,
but that said, the waste isn't nearly as big an issue as people are making it out to be. So like the waste product that we release into the air from coal is thousands of times more deadly and voluminous than nuclear waste. Like all of the nuclear waste we've ever had from even all this dirty nuclear fuel that was spent, everything the world has produced in the sense of nuclear waste would go a football field, like an American football field, 20 feet high stacked. It's a lot, but it's like 100 years of industrialization, and that's it. 20 feet high, one football field.
Now,
because we're getting energy from atoms, not from blocks.
Now, one of the things when like London, for example, during the height of the Industrial Revolution in the Victorian period and up to about the 1960s was, just burning coal constantly, wood and coal. And what was happening is you get a lot of, asthma, you get a lot of COPD, you get a lot of everything.
Cystic fibrosis.
You get like congenital disorders, you get like heightened psychological conditions, you get all this stuff. And the contamination
of your water sources from the plant, because the plant uses chemicals and water to make that fuel and to clean their equipment and to extract coal.
So like the London fogs were, they were these toxic smogs that were going around because they're like people were dying just breathing in the air. And now you get this in places like Beijing nowadays and all the industrialized third world, like in China and India, Indonesia, who are burning this stuff and not caring about the consequences of that, because it's just air. You can't. There's no concrete block that you're saying, oh, this is dangerous waste. But if there's one concrete block, but if what you have in these industrialized centers that aren't caring about what they're burning, you have thick smog covering an entire mega city, which is causing damage to millions of people all at once.
Not to mention climate change and the jet streams taking it across continents. Like, it doesn't just go away; it stays in the atmosphere.
No,
like you'll find it in the glacial glaciers, even in Sweden and stuff, which is really cool, kind of.
So that's like coal is definitely more of a problem, and like clean coal, like whatever, even if it is clean, it's not cleaner than this will be.
And even if they were the same, though, I'd rather a ton of radioactive waste on a pallet than a ton in the air that's just circulating and I'm breathing.
Exactly.
It's way better to have it concentrated and controlled and contained than to have it just dispersed into the atmosphere.
Right. And wind and solar the efficiency numbers just can't compete with either of them. So, what do we do? Well, we have an answer right here. And to that end, what is thorium?
Okay, well, we'll get into that right now then. So we're going to be talking about fast reactors compared to thermal reactors, and they work kind of similarly, but they're kind of confusing just by the nomenclature. So a fast reactor works quicker because it can use those fast neutrons. You don't need as much of a moderator, but also because they operate at higher heat, they're more efficient just inherently by the spectrum of heat output if you look at the charts and graphs of how energy is produced from fission. So you can try to burn more fuel, including like U-238, and it creates actinides just the same, or actinides is just another way of saying the byproduct of the waste. You can create actinides from neutron absorption while releasing energy, and this is done by reducing moderator and coolant demands using molten salts or metal at low pressures instead of at high pressures like you need to keep water in a liquid state while you're overheating it. So if you keep water in a state overheated, the most you can put it at is about 300 to 400 degrees Celsius without needing more than like 70 atmospheres of pressure, which is enough to make those explosions when they breach. But when you don't have that pressurization necessity on there, you can run at the most efficient rate of fission reactions, which is closer to the 500-600 degree range. And you can do it safely because any containment breach will instantly cool from the air and harden and solidify like we talked about before. Not to mention the freeze plugs, which will melt and drain if there is a meltdown event or some problem. The way thorium reactors work is slightly different than even just regular fast reactors. But I want to focus on thorium just A, for the time, and B, for it's the most effective method that we have so far that's known. Unless ITER works, because if fusion reaction works, then we might even have to skip all this. But in my opinion, you should probably have more than one source of power anyway. So
yeah.
I'll get into the thorium reaction process.
It'd be good to have both tools in our belt. Like the fusion does seem promising, and I'm actually, everything I hear about it seems very I'm tentatively optimistic, as I want to say, but the thing is that we have a technology that we can use right now. We can build it. We can break ground tomorrow. There's probably people who've been chomping at the bit with, their papers going like, oh, I've got the plans right here. I want to talk to the politicians in every country. There's just some physicist sitting in his room going like, ah. So we do need to keep throwing money into fusion because that's what we do.
That's the future of the future.
Yeah. So we need to keep pushing forward. Just because we have something just doesn't but
you'll still need power to create power, right? Like we're going to need the trucks that do the mining for all the metals and rare earths and stuff that build fusion reactors are going to need to be powered somehow. We might as well have them electrically powered by another reactor that produces less waste. Until we build nothing but fusion reactors in a few thousand years or whatever it takes, because they're really complicated. Again, it's like another order of magnitude more expensive to build these fusion reactors than it is to build regular fission reactors, but that's just because they're new. Like you refine processes and you make modulation and you compartmentalize everything into small chunks so that it's manageable to do at scale. But first you have to build it and then you have to solve all the problems from building it. And that just takes time. But with thorium, we could do it today, like you said. We have all the data we need. We've done all the prototypes. We've planned it for years. We've had scientists actually producing energy with these things. And if it weren't for them being silenced through NASA back in like the 70s or whatever, when they built the ERB, can't remember the name of it, but ERB1, I think, something like that. So yeah, we talked about the safety. Thorium works in the same way as all these other molten salt and metal reactors, in the sense that they got the freeze plug and they've got low pressure, higher heat for better efficiency and all that. It's passive, so it's like walk-away safety. You can build them small and modular because you don't have the pressurization requirements that you have with the thermal reactors with just water. The safety, an additional safety measure of these is they have, as I sort of mentioned to earlier, or alluded to earlier, in the event of a power outage or a tsunami or something like that, the moderators that are suspended inside the reactor core that help sustain the fission reaction process, they're held on by electromagnets. So when the power gets cut, these magnets lose their magnetic strength. They drop the moderator into the core, and then it helps the core not overheat because it's slowing down the process. You're not regulating anymore, you're just flooding it with regulator, moderator. So that safety system alone, but in tandem with the molten salt and the low pressure and the freeze plug, we've already got 4 redundancies that work better than the best redundancies we have on the current thermal reactors. So I really want to point out how much safer it is than the reactors we're already building, because it's insane that people are comparing them to nuclear explosions when it's just really frustrating to me. Anyway, so yeah, we have hundreds of them worldwide, bunch of prototypes, some research facilities. They work. There's no question that they work. There's tons of documentation. I've got some sources I'm going to list in the description for you if you want to check it out. China's been really good at checking into this, actually. They've some of the easiest information to find has been through China, believe it or not, because the government of the States has been suppressing it for so long. It took Kirk Sorensen to sort of be a whistleblower, because he used to work for NASA. So when they released the paper to NASA employees, and he's the one that spread it out to the public saying, hey, everybody should see this. Why are we hiding it?
Yeah. Well, China wants to look smart, so they'll be like, oh, look, we know what we're talking about here. Here's a bunch of papers. So
yeah. Well, the thing is, they're forward thinking. Like, they've got a dictator who can actually think 20 and 30 years down the line. And he wants to be remembered as like a genius leader, right? And to do that, you need to make big plans, but they have to make sense.
Yeah, like invade Taiwan.
Well, to the Chinese people, that makes sense because they think it's theirs already, but I don't even want to get into that.
Yeah, I know.
So for light water reactors, to run efficiently, they need about 70 atmospheres of pressure, like I sort of mentioned before, 250 to 300 degrees Celsius. Fukushima Daiichi was a gas explosion, yada, yada. I think we covered all that mostly. Mostly. Oh, yeah, that's the other benefit too. Molten salts and metal. I told you that they can run at higher heat, which is more efficient, but they also have a higher range of heat that they can operate in. So even if there is an issue or an error, you have much more time to react to it because you've got like 1,000 degrees Celsius range of acceptable temperature, as opposed to just like 50 degrees exploding the cap on your pressurized vessel through the water thermal reactors. So fast reactors are not only more efficient, produce less waste, they're safer ×4, but they also give you more time to react to a catastrophic failure, which is like just more than enough reason to pursue, in my opinion. But we talked a bit about the waste and the drain tanks. So if you want, I'm gonna maybe just post a link to some of these graphics, and they're just sort of like the breakdown of how thorium splits or becomes other products through the fission reaction. But I'll explain it briefly just because there's a point of note on here to state about the weaponization of the byproducts. Whereas the other nuclear reactors, they're actinides, the waste. One of them was plutonium from when the uranium absorbs a neutron instead of splitting from it, and that could be used to create weapons, so they can weaponize the waste. Whereas with thorium, it first converts itself upon taking in one neutron. It splits into 2 or sometimes 3 other neutrons to sustain the reaction, but the thorium itself becomes protactinium-232, and then that degrades after about 30 days to uranium-232, and then that degrades to thorium-228, and then thallium-208, and then down to plutonium-208, which is not useful. The uranium-232 is really important, though, because that lasts about 70 years, I believe, and that impedes weaponization of production of bombs and stuff. So it's not just that it can't be used for it, but if there's even trace amounts of it in your waste product that you're trying to repurpose into a nuclear warhead, it'll actually prevent the warhead from functioning properly unless they separate it and chemically distill it out, which is, again, labor intensive. They might as well just make their own enriched uranium. So it's not even worth stealing, basically. But this only happens through the thorium reaction chain. It doesn't happen through the straight uranium or the water or plutonium chains. So thorium has the added benefit of being less weaponizable, if that's a word. The protactinium, one of the downsides to thorium, though, is that you have to wait 30 days for it to decay into the useful uranium-233. But not such a big deal, because once you've got modular or scalable operation, you just have one tank every week sitting there fermenting, basically. It's kind of like a brewery.
So that would only be a problem for the first month.
Yeah.
And then so it's like, but that's 1 month. That's it.
When it takes you 15 years to build the facility, it takes 1 month to start, and then you
can have it show up a month early.
Yeah.
So,
or you can have it sitting there waiting even while the thing's still being built, and then if you don't use it, you don't use it. Whatever, you just re-enrich it if you need to. Like,
yeah.
So the fission products that you can use from the thorium chain reaction, you'll get sometimes an absorption, and sometimes the neutron will split and produce 2 more neutrons to keep going. So it's uranium-233, 235, 238, plutonium-239, and plutonium-241. Don't have to memorize that all. I'm just describing the fact that you're getting fuel out as your waste product. Even after you've produced energy, you use that to produce more energy. So it's sort of like eating to get fuel into your body and then eating your poop again, to put it grossly.
It's kind of that one scene in The Martian where he's taken all their the crew's solid waste and using that to
that's a much better analogy. Yes, it's like fertilizer.
Yeah. Night soil. Don't use it. Only in an emergency. So what we have here are viable alternatives. And to me, this sounds like win-win-win, because you have, I'm living in Alberta and everyone's talking about oil and whatnot, and I'm not against oil. One of the reasons I'm not against oil is not going away because plastics are infinitely useful. Anything that's oil-based, just, we don't like the idea of just putting oil waste into the air. But, we have tons of oil-based products that are better, cheaper, easier because we use plastics. Like not everything needs to be carved wood or stamped metal or something. And so the oil industry is not going to go away. It might shrink. But the other thing is that if you're worried about, I work, I don't want to lose my job, this will create new industries every day. So, some people need to build those reactors. We need more engineers, new engineers who understand this stuff differently. We need, recycling nuclear waste is an entire industry in itself. This is going to, you build a nuclear reactor in a town, and that town now has its own industry when, it's not sleepy anymore. So you're not getting rid of all the thing. Now, maybe coal might hit the road, but like, we're not going to be burning it in that amount. So what's the problem there is, we're still going to use coal for like coal furnaces and to cook pizzas, but that's like not even 0.5% of the coal usage. But the industries will be there. And
They'll actually build even more industries. They'll need more teachers to teach more people to have highly educated jobs. Thorium comes from the dirt everywhere on the planet, so there's no scarcity. You don't need to ship it across the world. You don't need to refine it or anything like that in out local places. All of your local jobs for the entire nuclear process here for nuclear power generation can be done locally. That includes right down from the mining all the way up to watching the systems. And instead of pumping oil on a rig in the middle of BF nowhere, getting, risking losing life and limb and braving the cold, your job will be to sit in a facility that passively safeties itself.
Right.
You'll get paid the same amount of money to sit there and watch a machine not fuck up.
Well, and the efficiency of this will allow us to engage in new, because there's been a few technologies that we also have that unfortunately need large amounts of efficient electricity generation. And one of the first one that comes to mind is desalinization.
That's a huge one.
Right now in places like Chile and all over the Arab world and Saharan Africa, the problem is getting water because there just isn't any. So if you're by the coast, what you do is you desalinate the ocean. So this gives you two things. This gives you water and salt. But the thing that you need to do to change this, to make this reactor, is to add energy. This chemical reaction is to add energy to it. And that's where the whole process becomes prohibitively the cost of it becomes prohibitive. So when you have a nuclear reactor in town, then it ends up like you have this constant stream of cheap electricity coming in. You can now you can now bring cheap water to cities and countries that would not have had that. Right now, like Dubai is spending billions and billions and billions of dollars on energy for their desalinization when they don't need to. They can do it cheaper. And
the biggest thing to that is irrigation, because once people can irrigate their land with so much abundance of fresh water, they can farm for themselves. And then you're not sending food from over another country all the way to you and burning all that fuel in transportation. Like it's all these compounding effects of having a localized economy that help it.
Or how about this? Mixed, we have these new LED lights mixed with a constant power source. Now you can do hydroponics cheaply and effectively and efficiently, and there's not as much what do you call that stuff? Inefficiency in the realm of thermal waste. So just heat, build up because the energy needs to go somewhere, but you still need the power, and the light bulbs aren't going to be exuding as much heat anymore because they don't need to. It's just the nature of how those light bulbs work. So now we have this other industry, this new farming technology where we don't have to use up all the land. We can, build down or build up and just have, that skyscraper is full of farms.
Yeah.
And
it would be feasible.
Yeah. It's completely feasible now. All we need is the energy. And
the other big thing along that line too is carbon capture.
I was just thinking that.
Oh, yeah. Sorry. I'll let you.
Yeah, no, go on, because you were.
Sorry, I get so into this stuff because it just drives me crazy that I'm not already doing it. But like carbon capture, if we want to reduce emissions and we can't find ways to do it, even if you build this power plant, you can use that power to reduce carbon in the air. So not only is it not producing carbon, now it's reducing the carbon that's already in the air, trapping from other nations, or even from your own country if you really have to. So you've got farming, irrigation, potable water. You've got better jobs that are easier to do that pay just the same. You've got a higher educated population. And from all of that, you get a locally sustainable economy that doesn't rely on imports from other countries. You're not shipping stuff across the ocean and, wheat to Italy from Canada. Like when you think about it, that's pretty crazy. All they need is power so that they have more water so they can grow it themselves.
Yeah. And carbon capture needs energy because you are taking it out of the air. And so the thing that you need to put into it is energy to have that change, to have that chemical reaction happen. You're changing something. Change needs energy. And
I think it's even just a pump. Like it's reverse osmosis of the air.
Right. And we have so much use for carbon. Like, and if we just pull it out of the air, you have these carbon farms, and then you have all this carbon that you can do whatever with. Like people,
graphite, nanotubes. You can make moderator out of it.
Make diamonds, whatever you want.
Like parts for your facility can be built out of the waste that you pull out of the air.
Yeah,
pretty crazy.
Now the other thing is that with these facilities that produce more on less land, what happens is we have less need for the land that we're using. And then we can let nature reclaim a lot of the land that we no longer need to, set aside like huge, multi-football field areas for parking lots and solar farms, which are nice and they feel good to make and they're great. And, my energy comes from the sun, but they're not efficient. It's not you're not getting what you want out of it. And wind farms feel good, but there's a lot of oil that goes into making those things and they're not clean. And
they're good. Like they're good.
They're good. It's not bad. We do need the energy, but it's not a solution. And
hydro is not really a solution either when we're dealing with climate change, because the problem with hydro dams is if you need the power, but there's not enough water in the reservoir, you sacrifice one for the other, right? So it's more sustainable and easier access to have a dam than to have wind or solar, granted, but only marginally so. You still need nuclear power as a stable backup to when your dams, you don't want to empty them.
Well, the problem is that with hydro, like it seems like it's an ecological good, but it does a lot of ecological damage. On top of that, if you look at something like, so you create this lake behind the dam and it kind of messes up the thing. Okay, well, nature will get over that. You're killing a lot of fish as they go through. Okay, that's a little bad. Okay, but the problem is that what happens when something like Lake Mead at the Hoover Dam dries up? If you look at pictures of Lake Mead, you can see where the water used to be, and then you can see tens of meters down where the water is now. How long is the Hoover Dam going to be viable in a drought area as a hydroelectric dam when there's no, hydro?
The Yangtze River is a really good example, and so is the Nile in Egypt.
Yes, the Aswan Dam and the Three Gorges Dam are the Yangtze River is not the idyllic spot that you think it is anymore because of the Three Gorges Dam, and let's just hope that
and the hundreds of thousands of people who got displaced to feed it.
Yeah, and they're building another dam on the Nile, I believe, or it's already done.
Yeah, Ethiopia is still fighting with Sudan and
that was it. Yeah,
Egypt about it.
So. You get these things and they have massive impacts that you can see from space on the ecology of the land that you build it on. Now Manitoba, I know where I'm from, has a lot of hydroelectric dams, especially in the central eastern portion of the province, because they have so many rivers. There's just hundreds and hundreds of rivers. Manitoba it's just got tons.
A dearth of water.
A dearth. But that area of Manitoba has to suffer for that. Now, where can we? I think I've beaten this horse a bit, but where can we go from here?
I think it's really important because the ecological benefits to nuclear power, a lot of people are denying nuclear power because of a perceived ecological loss. Mm-hmm. And that's just patently false in my opinion. Again, I'm not a nuclear physicist or anything, but the nuclear physicists that I read, it's not like I'm going out searching for my bias. I have no inclination whatsoever. I'm just information that I find, and that's all I can find is that there aren't net negative nuclear benefits relative to the things we're already doing. So maybe we can take a break and we'll start getting into the opposition of.
Yeah, I would like to get into that.
Specifically, Dr. Lyons.
Okay, I'll quiz you on that when we get back. Join us for part 2, and if it's not part 2 and we put them together, then this will be edited out.
Yeah, it'll put together. Dos coming at you.
Okay.
Hasta luego.